All right, here we go. Recording has started. Welcome everybody to the OpenShift Commons Validated Patterns Special Interest Group call. My name is Martin Jackson. I am a software engineer on the Validated Patterns team. I've got my Validated Patterns t-shirt and my Validated Patterns triangle to establish my credibility in that regard. And I am here to talk about GitOps and secrets, which is kind of an interesting thing and has an interesting history in terms of how the framework has developed its support for secrets. And I've got some fun things to talk about some of the things that we have that are cooking and will soon be delivered in terms of how the patterns framework handles secrets. One rule of thumb, if you have a question, please feel free to put your hand up in the presentation. I'll try and deal with them as possible. I think Anthony's probably going to help try and wrangle some of that stuff too. But the whole point here is to have a conversation. I've got a bunch of things to say, and I'm hoping I can get through it all. But the really important thing here is to engage in dialogue and to learn from each other, because like you can read the slides anywhere, but we come to these SIG calls to have conversations. So with that, let's get started. Okay, first off, just to give you an idea of some of the material that we're going to cover. We're going to talk a little bit about some of the foundational principles of GitOps and how secrets relate with those. Because that has everything to do with how the validated patterns framework in particular deals with secrets. We're going to talk about some approaches and strategies in the real world for how people manage secrets in GitOps. And then we're going to talk about how the validated patterns framework deals with secrets, because we have to take a position and we have to be opinionated. That doesn't necessarily mean that our way is the only way, but you may find it interesting to hear some of the thought processes behind why we're doing things the way we're doing them, and possibly even have some suggestions for us on how to improve them. And finally, we're going to talk about some things that are actually in the process of development for the validated patterns framework and its secrets handling, because I actually have some deliverables for this quarter that relate to that. Which is one of the reasons I volunteered to do this talk, and Anthony can keep me honest because he's our product manager. So first off, let's talk about GitOps and secrets. The most important thing about GitOps is that when we follow the GitOps methodology, what we're trying to do is to record all of the details of our deployments and our operational parameters as code in a Git repository. And that Git repository is supposed to be completely definitive and authoritative for everything that's going on in the deployment. We treat everything as code. Git is the source of truth for that code. If it doesn't exist in the Git repository, if it's not on a branch, it isn't there, period. That's how we think about it. And then when we need to change aspects of our deployments, if we need to add an application, if we need to scale infrastructure, if we need to change how load balancers work, then those things happen through Git workflows. There's a pull request that's submitted to the repository that has the source of truth. And by merging the PR to the Git repository and the source of truth, that means the source of truth changes. We expect the deployment to change. We expect reality to follow that deployment, right? That's wonderful. When you're talking about how many containers you should be running, which container image you should run, all of that stuff is, public information and is not particularly worrisome if that gets into the quote unquote wrong hands. And so to describe that, more theoretically, by putting all of our state and encoding all of our state in Git, that means that the system is described declaratively. We're not using aspects of the system to introspect it and to say, may I do this thing? We say declaratively, this is what the state of the system should be, and we have a thing that is in our GitOps inventory that is responsible for making the state to be what we have declared the state to be. That desired state is versioned in Git. And so if it isn't in Git, it doesn't exist, period. Approved changes can then be applied automatically. That's another way of restating the the Git workflow thing. And then the controller exists to detect and act on drift, which means you have something that is continuously running that looks at what the desired state is and what the current state is. And if there's a discrepancy between the desired state and the current state, then that controller exists to try and reconcile that difference, to apply that change and to make it so that the desired state is the running state. And all that's well and good when you're dealing with public information, container images, potentially versions, the number of containers you're running and everything. But it's a real problem when the thing that you are, that is part of the desired state of the application is an actual secret. So when we say secrets, what do we mean? There are lots of things that qualify as secrets. Fundamentally, it is any piece of sensitive information. And if you want to be quippy and glib about it, it's basically anything your security group doesn't want anybody else to see, or anything that you as a responsible system administrator know that you wouldn't want posting on a public forum somewhere. You don't post your root passwords out there in Git for people to download and use, because that makes an attacker's job way too easy. So there are lots of these different kinds of sensitive information. We've got usernames and passwords. We've got certificates. Not the public part of the certificate, but the private key part of the certificate is definitely secret information. Because if you have the secret key for the certificate, you can impersonate things that you should not be able to impersonate, and so on. And secrets have many formats and can take on many forms. In almost all cases, a secret is different per deployment. So if you've got two different deployments of the same application that are sitting behind two different load balancers, then there are typically two different certificates, one for each load balancer group, that identify that application. You, generally speaking, do not want to deploy exactly the same secret for exactly the same application in many different instances, because that, again, lessens the attack surface for bad guys and people who want to steal your information or do other things. So we want to make it possible to manage lots of different secrets, but we don't want to put those secrets into our Git repositories directly. That's problematic. Another characteristic about secrets is that typically workloads don't do anything without them. So often the secrets are essential to the way that the workload runs. If you've got something like a database or cache password, the application cannot function without the database connection string. It may be able to function, but would be very impaired if it isn't able to talk to its cache. And so these workload needs are vital to the way the application works. And it's not like if we could avoid having the secret, we would avoid having the secret, but we need to have the secret in order to use it. And finally, the other thing about secrets is that because there are so many different kinds, and because they've got different names, a username is often, a password is almost always called a password, but usernames can be called other things. SSH keys can go by multiple names. And sometimes when applications are deployed, they need to use different names, different field structures. You need to have a lot of flexibility in how you present a secret to an application, because applications are often very, very opinionated about the format and the contents of the secrets that you give them. And so you need a lot of flexibility to handle them. Now, the great thing about Kubernetes is that Kubernetes provides a wonderful secret object. The secret object in Kubernetes can be encrypted at rest inside etcd in your cluster, which makes it safer from prying eyes. But the secret object itself does not actually encrypt the secrets that you give it. The value part of the secret is base 64 encoded, but that is not encryption. That's basically just obfuscation. So you can't literally copy and paste the thing from the secret value and use it, but it's a literal hop, skip, and jump away from being able to decode it and pass it into the thing as an actual credential. The cool thing about Kubernetes secrets objects is that they provide all this flexibility for these kinds of multi-field objects. And there are a couple of built-in secrets type in Kubernetes, like the basic HTTP authentication type, which is used all over the place, the SSH key. There are certain kinds of labels and annotations that you can give to secrets that give many applications hints about how to use them. But there are almost as many different ways of using secrets as in Kubernetes as there are different kinds of secrets objects. And so anything that we use systematically in Kubernetes has to preserve all of that systematic flexibility that we need, and still has to be able to keep the data that we need to stay hidden. And so that means that the one thing that we cannot do in GitOps is to include unencrypted secrets in public repositories, because that is too big of a security risk. It should. It doesn't. Older versions, question came up in chat. I don't know what the current default in OpenShift, for example, is, but it is, I believe it's just a config map that you set when you set up a cluster that determines whether or not the etcd is encrypted at rest. It is an easy thing to do, and you should do it, but I don't think it's mandatory.
I'm just going to throw this question out there to you, Martin and Anthony, is, being that the chain of trust from, your secrets and that type of thing, if you break that chain of trust, where is that security mechanism regained? Meaning that if it says can encrypted versus shall, or should or shall, because your secret should be, like we're talking about, protected. And so if we don't protect them, from start to finish, and if those get breached somehow, where do you get that chain of trust reestablished, if possible? Does that make sense?
For the most part,
you didn't start with encrypted, so it said because it says can, you didn't start encrypted. Where does that encryption slash security, I can't think of the word right off the top of my head, gents, go into that play? Does that make sense?
Yes. If you have, by default, secrets are only exposed to people who have administrative level access to the cluster. And then administrators of the cluster can expose or provide read access to those secrets as needed. If someone who is unauthorized gains access to those secrets, best practice is to basically burn all of the credentials that have been compromised or could potentially have been compromised, revoke them using whatever scheme is available. You can expire a certificate, you can revoke things like AWS credentials, you can revoke certificates of various kinds. You can often blacklist or deny list SSH keys, but that's what you have to do. And when there's a breach, if you know there's been a breach, it's a pain, but it saves you a lot of trouble down the road, because what can happen is that if I have stolen your secrets and I'm a bad guy, the last thing that I want you to know is that I have in fact stolen your secrets. And I am going to keep using those secrets for as long as I physically can until those secrets have been revoked. So, generally speaking, someone isn't going to put their hand up and say, "Hey, I stole your secrets." They're just going to use them in unauthorized ways, and you're going to see things like your AWS bill skyrocket.
Right. Right. And the question I'm saying is I understand, the remediation after the fact.
Yep.
But what I'm getting at is before the fact, of making sure, that those secrets are encrypted. So if a person does get that, they're not in the they're not able to, expose or use those secrets to, get to my system. That's what I'm getting at is, you use as it should be shall or should, because then that builds that extra layer of security so that if, heaven forbid that, those secrets get exposed, then it's kind of like, I know I'm going to, get yelled at for this, but like BitLocker on your laptops or Lux. If I pull that hard drive out and put on another or a slave or whatever, I'm not going to be able to get in there either without a password or some type of security key. Same thing with the secrets. If I take that secrets and put locks on them or something like that where they can't get to it, then if I pull that out, somebody gets in there and pulls that out, they still can't get into that and use those secrets in my system. And so that
Right.
chain of trust is already still verified and still still there. And it's not did I or have I or should I did I do this or did I do this? It's already there. It's already included within the installation or the setup, etc. So that is currently there. I mean, I get what you're saying, Martin, is on the aftermath. I don't want to get to that aftermath. I want to be able to Lux or BitLocker that capability already in play.
Yes. If the cluster data in question matters to you, we are absolutely in favor of and would unreservedly recommend that you encrypt them at rest. We don't force you to do that, but it is most certainly best practice to do so. And I certainly wouldn't want anything I'm saying to suggest that that's not the case. Defense in depth is the order of the day, and we take secrets very seriously, and everything. We believe that you should do everything that you can do to protect those secrets, because dealing with breaches is not fun, as you said.
I'm good now. Sorry, gents. I just
Sure,
brought that
sure.
up because it was from a security standpoint that's a kind of a big deal.
It is. It absolutely is. All right. So we have a bit of a dilemma here. We want our state to be stored in Git. Secrets are part of the state of a running application, but it's unsafe to store secrets unencrypted in Git repositories. And so that leaves us with a sort of operational problem that we have to solve. And generally speaking, there are a couple of ways to handle this problem operationally. Either we can tokenize secrets in the repo, which means that we have a placeholder inside the repo that represents a secret, and then we use some kind of external system to replace the token with the actual secret in runtime. Or we encrypt the repo itself, or we encrypt the secrets inside the repo. There are a number of solutions to both approaches that are running out there in the real world. On the pro side of tokenizing, when you're looking at the difference between two different Git repositories and a change, the diff is a lot easier to read and understand if the contents of the repository are not encrypted. Otherwise, you just have a bunch of gunk in the repository, a big, 2,000 character string of base 64, encrypted stuff. And you just see blobs that are changing in different places. The con is that it's a bit more complex to implement. It requires a separate secret storage engine, and you don't necessarily want to lock yourself forever into the use of a particular secret storage engine. Some of the secret storage engines that are available include HashiCorp Vault, the AWS Secrets Manager, the Azure SDK, CyberArk Conjur is also popularly used in a bunch of places. And I am not endorsing any of these solutions as an employee / associate of Red Hat. I'm merely pointing out that they exist. Where I used to be, they were very sensitive about the notion that anyone who put logos on a slide was doing endorsement. This is not endorsement. This is just a survey of some of the solutions that are available. Now, on the other side, encrypting the repo and encrypting the secrets inside the repo. It is a simpler thing in many cases to implement because basically you're just running things through a GPG key pipe or something like that. And it doesn't require an external tool typically to manage. But on the con side, if you only encrypt secrets, you have to work out when and how those secrets are going to be encrypted. And so that's a workflow challenge. And then you still have to manage the decryption keys somewhere. And typically the decryption keys for these kinds of secrets have to be deployed pretty close to where the secrets themselves are going to be used, which means that operationally it's often relatively easy if you get access to the encrypted secrets inside the repo to be able to figure out which key is used to decrypt those secrets. And often in most of the runtime scenarios, it's pretty easy to put those things together. So if you compromise the system, you don't have to compromise both the secret storage system and the repository. You just have to compromise the repository and the running system around it. Now, out there in the real world, there's a project called Kubernetes Sealed Secrets that takes this approach and is a nice kind of packaged approach to this problem. So, in broad terms, there's lots of nuance to this. There's a lot of subtleties, the different approaches, but these are the two fundamental different approaches to the problem. On the validated patterns team at Red Hat, we are absolutely on team tokenization, though. But committing to team tokenization means that we still have some important decisions to make. Because there are a bunch of secret providers to choose from, we have to choose one or more secret providers to use. And we also, have to make it easy for users to handle secrets because every different secret provider has a different way of storing secrets, loading secrets, and so on. And also, it's kind of the responsible thing to do if someone wants to use a different secret provider to make it easy or at least possible for them to do that. And so that's the main reason that we have taken the approach to secrets inside the validated patterns framework that we have. So the linchpin of the validated patterns approach to secrets is something called the external secrets operator. The external secrets operator is a wonderful community project that can create arbitrary Kubernetes secrets objects from key material that's stored inside of several different potential key stores. It works with all of the major popular secret storage providers, which includes all of the list of the other ones that I showed earlier. Vault, Conjur, AWS, Azure SDK, also GCP, Alibaba, the IBM Secrets Manager, and several others. So it will work with whatever secret provider, almost whatever secret provider you happen to want to use. And it can then create secret material, secret objects inside your cluster out of that secret material and project them into the namespaces where you need them. This is, we think, the best approach to being able to manage your deployments in Git, and then you manage your Git secrets, your secret material out of band of Git using your secrets provider. But then you use the tokens in your Git repositories in order to project those secrets into your applications and run them. so that your secrets do not have to live in your Git repositories, but the pointers to your secrets and the tokens that represent your secrets do live in your Git repositories, and you can still reason about how your secrets are changing and so forth. So in our case, the external secrets operator is important for that process because it allows for flexibility in which secrets backend you use, and allows you to choose your own secrets backend and how you're going to store your secrets according to your operational needs. Now, a big note here is that as of December 12th, 2023, Red Hat does not support the external secrets operator as a Red Hat product, which has a lot of special definitions, in terms of how your support agreements with Red Hat and other companies work. Now, the external secrets operator does have many fans, publicly avowed fans within Red Hat, and it is quite possible that that situation will change. But as of right this moment, Red Hat has not publicly announced support for the external secrets operator as an official Red Hat product. So I have to provide that caveat too. That situation can change. I hope it changes. I'm advocating for it to change. But as of today, that is not the way things are. If you want to pay Red Hat for support for the ESO, you cannot do that. But everybody loves the ESO, and we're really, really hoping that we can get that included in as part of a Red Hat product in the foreseeable future. We're hoping to. We haven't achieved that yet. If that changes, the SIGs will be one of the first to hear about it, I'm sure. All right. Now, with that said, we can talk about how the validated patterns framework handles secrets. Like I said, the linchpin of the validated patterns secret strategy is using the external secrets operator. And the reason for that is we don't want to force users of the framework to use a particular secret store or a particular or be forced into a particular operational approach that way. And we think that the ESO, despite the fact that it isn't officially supported by Red Hat yet, is the best way to get that outcome. The way it works is that for the validated patterns framework, the code to manage the external secrets operator lives in our common repository, which is part of all of our validated patterns. We have defined our own file format and our own utilities for representing secrets, which provide a number of convenience functions that allow you to point to files, to extract elements from files, basically so that you don't have to replicate your secrets in a lot of places. And we also provide integrated support within that file format for encrypting that file at rest, so that, ideally, you've got BitLocker or Lux encrypting your hard drive, and then you have an additional password that is required to gain access to the vault where you have the credentials stored for your validated patterns, so that a single compromise is not sufficient to disclose all of the secrets that you have on your machine. We provide a process within the framework for injecting secret material into the secret store as part of pattern installation. And we also support that injection of secrets can be done out of band at any time after installing the pattern. So if you need to rotate keys or something like that, we have a straightforward process for you to inject the new keys into the framework, into the pattern. And all OpenShift, all Red Hat OpenShift validated patterns support this scheme today. Talking about the file format a little bit abstractly, it describes a series of secrets. And so there are an arbitrary number of secrets, and every secret has a number of fields. A field has a name and a type. So a value is a literal string. That's easy. That's like a username. It would be field username value and the value for the username field. Field password and the string that goes along with it. But in addition to just values, you can also have a path type, which will instead of containing the literal text that will be injected into that field, can point to a file. And the file's contents will be the value for that secret. So this is particularly helpful if you're injecting SSH keys as secrets, instead of having to figure out how to correctly format your SSH private key for the purpose of injecting it in a YAML file. You can point to where that file lives on disk and give it that reference. And the secrets loader will read the file, inject the contents of the file for that field. Everybody's happy. We also have an any key type, which can retrieve data from an any file. The main place that we use this is for AWS credentials. And like the worst thing is to have lots of different places where you're storing AWS credentials, because there's almost nothing that you can make as much mischief with as you can with AWS credentials. Spin up a bunch of machines, do a bunch of work on somebody else's credit card. It's a bad time. We did not want people to be able to be forced to update multiple copies of their AWS credentials and so on. So we created this convenience mechanism to allow people to point to one source of truth for their secrets and be able to reference them in multiple ways. These are some actual examples of the way that these files and systems work inside the validated patterns framework. On the left-hand side, you see a manifest of secrets, and this is for our industrial edge validated pattern. The secret name is image registry. The fields that are required for the image registry include a username and a password. You see some additional things there on missing value. If the secrets file that you are pointing to does not actually contain this field for this secret, our secrets loading system will prompt you for what data should be entered in there. So you don't need to store it at all if you don't want to. And then same way with the password, there's prompt text. You can have custom prompt text. Otherwise, there's a default prompt, which will basically say for secret named image registry, for field named password, what do you want? And it will pause at the secret loading phase to get your input. And basically, the get secret works the same way. You see for the AWS secret at the bottom there on the left, the example of how we use the any file type. It specifies the any file and the any key, and by using these mechanisms, this means that you do not have to duplicate your own personal secret material. And we figured that this would be helpful and useful for people managing their secrets. On the right-hand side, we have an example of how the secrets file is used in the Ansible Edge GitOps pattern. This shows a couple of other options. If you look, you see at, okay, yeah, you can see my mouse pointer there. If you look at the bottom secret here, AAP manifest, you see that there is base 64 content that specifies a path, because typically a manifest that you will load into AAP is a couple hundred K, and you do not want to represent that in a YAML file. So instead of forcing you to inject that into a YAML file, you point to the path where that's going to be loaded, and it will using the base 64 attribute for the field, it will automatically encode that in base 64 for you before it injects it into the secret store. So those are, the convenience mechanisms that we use for the secrets framework, and kind of how they work. And we wanted to make it as easy as possible for people to use, and solve actual problems that people would have, deploying these things. And so, yeah, that's how it works. Any questions about any of this so far? All right. The way that the ESO itself is used within the framework looks like this. We've got a couple of different examples for how we use this tokenization approach in actual validated patterns again. And here we have examples from Industrial Edge and from Ansible Edge again. The ESO uses the kind external secret. And so by declaring an external secret kind, what that basically does is it defines how and where the external secrets operator is going to pull the secret material from. And it also defines the kind of secret that it is going to create in the target namespace. So the secret store ref, you have to have set up a secret store previously using the ESO. But you give the secret store a name, and you give the secret store a kind, and that is basically your reference. That's all you need to know from for the purpose of creating the secret store. The target defines the secret object that you are going to create from that secret material. You have to give it a name, and then the template will allow you to define extra annotations if you need them. It will allow you to declare a type. And then the data that goes into that secret is typically an extract. There are some other options. But when you say extract key, it will take all of the fields and all of the values from the key that you give it and turn that into the data of the secret type. So it's really straightforward to use once you get the hang of it. And some of the hard things that you have to do sometimes in constructing secrets, the ESO makes really, really easy. I don't have enough good things to say about ESO. It makes life working with secrets in Kubernetes much, much nicer. On the right-hand side is an example of a slightly more advanced use of an external secrets object. We've got some sync wave stuff going on. We've got the secret store ref like before, the name and the kind. Another key operational aspect of external secrets is the refresh interval. The external secrets operator's job is to make sure that the secret object is constantly up to date. And so it has a default refresh interval, but you can also set one so that if that secret is rotated, any Kubernetes object that depends on the secret object being up to date will see that the secret object has changed. That can trigger redeployments or other operational things within Kubernetes, again, making your life easier. And so the data can be more explicitly defined other than just taking a direct data from. You can refer to specific keys and properties if you want to filter out specific keys or properties. The ESO gives you all the flexibility you need. And there's also some built-in extra templating that I thought might be a bit too much to show in these slides, so I left it out. But if you can imagine that you want to do it with a secret, the ESO probably gives you a straightforward way of doing that. And finally, coming soon. As of right now, we built support into the validated patterns framework for using the HashiCorp Vault backend. The reason for using Vault was that Vault is an open source project. It is supported in all of the places that the validated patterns framework is supported. And it runs in all the different places where you would potentially want to run OpenShift or Kubernetes. So if you look at the other major secrets backends that ESO supports, many of them are hyperscaler specific. So you can plug into the AWS Secrets Manager. But if you're running your pattern on Azure, it doesn't make a lot of sense to store your secrets in Amazon Secret Manager for an Azure-based pattern. If you want to keep the whole pattern self-contained, it's a lot more straightforward to store all of your secrets in a local secret store. And so Vault was by far the most popular one that was available for all of those things, for all the different clouds, for bare metal. Vault was well documented, and so on. This was before Vault and HashiCorp in particular decided that they were going to change their licensing scheme. And so when Vault made when HashiCorp made their announcement about moving all of their products to the business source license, that triggered a lot of discussions internal to Red Hat, and a bunch of product decisions were made about just how much do we want to depend on HashiCorp products if they're going to be willing to change the licenses in this way. And to be very clear, the way that the Validated Patterns framework uses Vault is in compliance with the new Vault license terms. And we confirmed that with the HashiCorp DevRel team. There's nothing about the Validated Patterns framework that intends to supplant Vault or kind of fork Vault or create its own secret store. It's using the open source version of Vault as a secret store, which is the way that Vault, the open source version of Vault wants to be used. So our usage of Vault is compliant, but this led to a conversation on the patterns team about should we continue to only provide, to basically provide Vault as the only code path that we ship with our patterns as far as how these things should work. And the answer that we came up with was, no, we should actually provide some choice. And also architecturally, the way that we support Vault in our released patterns today, the way that we support Vault in our released patterns today makes it harder than it should be to replace your own, to replace it with a different secrets engine or to use the tooling in a different way than what we intended with Vault. And so with that in mind, I actually have a deliverable for this quarter to refactor a bunch of this code. And I'm a good chunk of the way through that to enable the use of other backends and other options. Oh yeah. VPs are absolutely open source. And nothing we're doing here or talking about here changes that. As in addition to our obligations to open source communities from the patterns framework standpoint, we also don't want to make things unduly difficult for people who want to be able to pay for support for validated patterns if they so choose. You don't. Now, the question in chat is, do I need a license? You don't. And we're making sure through our engineering that you don't.
But it says means if you deploy the HashiCorp Vault as a part of a pattern, you're going to need to deploy in production, need a license. And I'm like going, isn't it kind of productive from that standpoint? I could be reading it wrong, Anthony.
Their licensing terms is the problem. It's if you just deploy the open source technology, yes, everything is fine in open source. But from their perspective, the way that they have their licensing, depending on what bits you use to deploy, there is a measure of they're asking for people to have a license.
Okay.
Correct,
enough.
Martin. I don't want to speak out of turn, but this is the conversation we've been having with them. We're fine because we're testing. We're fine in a proof of concept or in a dev environment. But once you get to certain environments, their binaries, depending on where you obtain them from in their license change, they were modifying things. Is that wrong, Marty? I mean, there's been lots of conversations, but
it's there's a bit of ambiguity about it. Fundamentally, HashiCorp is a software company. They get paid by people who are paying them for support. Red Hat is a software company. We get paid by people who are asking us for support. And there are aspects of both of this. As Red Hat, we often wear two hats. We have the community hat, which is these are all the things that we are donating to the community that are that anyone can run for any reason whatsoever, and we're making the knowledge of how to run it available. We're making the actual bits that you need to run them available, but we don't necessarily take support contract money for paying for the exact bits that we ship as the community bits. And that's a lot of why this distinction exists as well too, because there is interest inside of Red Hat to make validated patterns things that people can pay for if they want to pay for. Like everything that Red Hat works on, you can get it, you can run it, but not necessarily, Red Hat doesn't support it in the sense that, you cannot pay Red Hat money to take those exact bits and, put in a support ticket and have an SLA for it, like Fedora. Fedora is mostly made by Red Hat. I run Fedora. I'm doing this presentation on a Fedora-based machine. In the broader sense, Red Hat supports Fedora in that Red Hat finances a lot of the development of Fedora and donates Fedora to the world, but you do not pay Red Hat for support for Fedora. That's not how this works. And the external secrets operator and HashiCorp Vault are basically in the same kind of position. That Vault, you can pay HashiCorp for support for it. The only version that we Red Hat are able to publish with the framework is the open source version, which they don't support in the sense that you pay them for support for it. And so untangling a lot of this mess was a lot of the motivation for developing alternative secrets backends. So the two main aspects of this work that I'm in the process of doing right now is to refactor the value secret parsing code, which currently is very, if you look at it in common, it's very specific to the way that Vault works, and is kind of hard to unwind from the way that you would need to inject secrets into a Vault secret store. The goal there is to disentangle that somewhat, to enable parsing of the value secret file regardless of where you want to put it, and make it easier to extend in that way, but also to allow you to choose a Kubernetes secret backend, which is also available everywhere. Basically, you inject secrets into a specific namespace and then project those secrets into a different namespace. Or since you're just injecting Kubernetes secrets, you can skip the external secrets operator altogether and just directly inject the secrets that you mean to inject into your cluster using this code base, and skipping all the potential complexity, but still preserving the flexibility and the benefits of the value secret format that we developed for the validated patterns effort.
Thank you, Marty. I was just, like I said, I didn't want to go down too much of a rabbit hole in that sense, but I'm just looking at it from, validated pattern, HashiCorp Vault, money.
Yep.
et cetera, et cetera. Because it's kind of like do we what do we do?
Yep.
In that respect, because we're in the process of doing, like, for example, I want to do a VP on a cluster or a container or whatever. And now I've got to stop what I'm doing midstream and buy something from HashiCorp and say, hey, this is what we want. Or if we buy it and we don't have maybe we don't renew the HashiCorp vault, where are those secrets at? Do I
Right.
get access to those secrets? Do I have to reinvent the entire wheel from a secret standpoint? Because maybe I found something different. Maybe I found this, and because that vault is within their purview / jurisdiction, whatever you call it. Do I have access to those? Do I have to now? Do I have to do have to rip out all that, kill it all, and then reload it? I mean, that's a pretty big deal if I have to redo all that. Basically, it's the same thing as it being a breach,
Yes.
for lack of a better term.
Yes, it is. And the operational details of how you have all that stuff defined, we looked at one of the major engineering efforts that we put into the validated patterns framework when we first started it was we knew that we had to come up with a better solution for how to handle secrets than what we had out of the box. And the Vault plus ESO solution is what we came up with as better than what comes out of the box. But over time, we wound up having so much wrapped around the proverbial axle of the Vault plus ESO solution that we wanted to be able to provide that level of flexibility and choice within the framework so that people would not find themselves in a position where if they had gone in with Vault, that Vault was the only possible answer that the pattern framework supported. And that's why we're doing that work now. Yep, good point. All right. That is the slide deck that I have prepared for today. Are there any questions or questions or discussions anyone wants to bring up?
So Marty, the ones that you listed, HashiCorp Vault, AWS, Conjure, are those the only vaults, the only secret stores we can have? Are there others that may be out there that we haven't tried? Or
Oh yeah. There's a list of about 10 total secret stores that are supported by the external secrets operator today. AWS, Azure, GCP, Vault, Conjure, 1Password, GitLab's project variables scheme is also supported. IBM Secret Store, Alibaba, Tencent, and people are working on adding other secret backend support, secret provider backend support to the external secrets operator as we speak. In fact, support for CyberArk Conjure was only added within the last 6 months, and basically, if it's a major secret store that's widely used on the internet, you can reasonably expect that the ESO has support for it. Yes, Shanna?
Oh, hi. Yes, thanks for the presentation. It's very useful. I have a customer actually using Vault, like the open source way, right? The HashiCorp one. And what would you think is the best recommendation for them to looking forward if they should if they're not gonna to, if they don't want to use the license in the buy the license in the production, what would you recommend them to do?
Well, organizationally, this is a big organizational question because any secret store kind of question is going to be very tied up in what that organization is, permitted to do based on the audit requirements that they have to respond to, and potentially also any regulatory requirements that they have to respond to. And so they're like, if they are in a secret store that they are paying, if they're in a secret store that they're not paying for now, that suggests to me that either they're very early in the efforts, potentially they haven't had the audit and other organizations seriously look at a lot of these questions. But the most important thing is to be aligned with what security requires from that standpoint.
Okay.
If it's untenable for them to get a paid for support kind of vault product, and their operational parameters dictate it, if they're only in one cloud or one hyperscaler or something like that, I would, if I were in those shoes, I would take a very serious look at the hyperscaler based secrets provider, either AWS or GCP or Azure.
Okay, thank you. And so, like you mentioned that 2.0, I assume that's having that in mind, that 2.0 validated pattern will be, we will be able to implement the patterns by giving the customer or end users this choice of whatever store they want, right? That's the goal. Okay, I will definitely share this information on the pattern. I'm not sure they're aware of that, but yeah, good info.
There will be the major things that will be delivered in the next iteration of secret support for validated patterns will either be the use of the internal Kubernetes secret store backend, or not using any kind of secret store backend at all, but directly injecting secrets into the Kubernetes cluster. It is a relatively straightforward thing to adapt the framework to use one of the hyperscaler secrets providers. That isn't currently in scope for me right now, but that's something that we can definitely discuss. And if you're if this is an internal Red Hat discussion, we can carry this on internally, and we can talk more about it.
Sure, thank you. If you don't mind, I will reach out and get some advice from you. Thank you so much.
Certainly.
Martin. Appreciate it.
Yep.
And with that, we are at the top of the hour. A minute or so over. It's been a great conversation. Marty, if you don't mind, we'll probably package this up in a PDF and toss it into the notes so everyone can see it. And our next call will be, we're going to not be here the last Tuesday of the year. I think that's during one of our holidays off. So we will see everyone next on our call on January 9th. Thanks again, Marty, for a great presentation.
Very welcome. My pleasure to be here.
Take care. Bye.